So welcome everyone. Today we've got a QISS seminar, so Quantum Information Structure of Spacetime, hosted by Augustin Vanrietvelde on the topic of causal decompositions of one-dimensional quantum cellular automata. So the talks are typically approximately 30 to 40 minutes, and this talk is currently being recorded and live streamed. So for anyone in the audience, please feel free to ask any questions if you want anything clarified, especially on technical points that are being discussed. For more open-ended discussions, we have plenty of open-ended time at the end for longer form discussion. And so with that, I'll thank Augustin for agreeing to talk, and I'll give the floor over to Augustin and say, take it away.
Great. Yeah, thank you, Matt. Thanks everyone for being here. It's a real pleasure to me to be presenting this work, which I think has a lot to say about the interplay between quantum information on the one hand and the structure of space-time on the other hand. So I think it's a very fitting seminar to be presenting it in. Okay, so sorry. Yeah, that work is about ongoing work, hopefully soon finished, that I did with Pablo Urigi and Octave Mestoudian here in Saclay, next to Paris, for the past couple of years, in fact. So it's an ongoing work that is eventually going to lead to two papers that are tightly linked, one about the partitions of quantum systems, and one about the causal decomposability of 1D quantum cellular automata. And the idea is that the first one is a very general one, but it provides part of the theory that you need to describe the result of the second one. And if you are more interested in the first one, you can look it up on Pearsa. So here I will only be presenting it briefly. Okay, so to set up the broad map of what I'm going to talk about, I'm first going to embed all of this inside the picture of the more general quantum causal term that is currently going on, in my opinion, in quantum foundations. And I will, within this context, explain why causal decompositions are an important structural result, an important structural conjecture at the moment in that context. Then I will explain how to prove causal decompositions and really understand the core of their structure. You need methods involving sister algebras, and show how this in fact leads to many subtleties and ambiguities that require a theory of partitions. And finally, I will show how using this, you can finally state causal decompositions, prove at least some of them, in particular, those of 1D quantum cellular automata, which I'm going to present. And I'm going to briefly mention other possible applications of the same theory that I can think of. All right, so let's start with causal structure in quantum theory and why people have started to believe it is an important concept. So there are many ways that have led people into this emphasis on causal structure in quantum foundations. I like this one, which is about going beyond kinematics and dynamics. So this comes from Rob Speckens, who in a paper that I found very promising 10 years ago, made this point that in a usually presented physical theory, you have the kinematics, the structure of the state, and then you have on top of that, the dynamics, that is the structure of how the state evolves in time. And he makes the point that you can change the kinematics of the theory while changing the dynamics at the same time in such a way that the theory stays the same. So in some sense, there is some kind of gauge, if you want, between the kinematics and the dynamics in a theory. And Rob Speckens argues that it makes this divide kind of artificial. And what you would need is some union of them that is kind of gauge independent in a sense and describes an independent reality. And he pins down the notion of causal structure as providing a good characterization of that union. And a good way to see this, that also comes from Rob Speckens, among other people, is to see that the weirdness of quantum theory has a lot to do with causality, in particular the failure of classical causality. So when we think about causal structure, we can think of it in these very broad terms of saying I have a graph of nodes where I'm collecting data, and some of these nodes possibly I cannot collect data about, they are hidden nodes. and I want to figure out whether this causal structure is compatible with the kind of data I'm collecting at the node. So the question is, if I'm assuming this causal structure for the data, how does this constrain it? And this has been studied a lot in the past 50 years. A typical framework for this is the classical causal models of Judeo-Pearl. And a good way to understand the violation of Bell inequality is that precisely this is a failure of classical causal models. So if you feed, and this is presented in the paper I'm showing at the bottom, if you feed the observed data in a Bell experiment to some software for classical causal inference, it will tell you that the causal structure on the left cannot be the causal structure of the experiment. And it will tell you there must be some other layer going, for instance, from S to B. So this points to a failure of the classical causal models to explain quantum theory. One response to this has been to say that we have to bite the bullet and we have to create quantum causal models, models of causality that are natively built on the features of quantum theory. And one proposal is to build this on the case of unitary channels. So you can then say that a unitary channel with several inputs and several outputs, so here in a simple case of 2 inputs and 2 outputs, can have a certain causal structure of saying a certain of its inputs doesn't affect a certain of its outputs. So for instance, you can say that A here, which is an input, doesn't affect the output D through the unitary channel. There are many ways of defining that. A typical way is to say if I discard C, so this is a trace out that you do on C, this is the same thing as if I discarded A in the first place because A now has nowhere to go. And there are many other possible definitions and they all turn out to be equivalent, which is testifying to the strength of this notion, to the robustness of this notion. Okay, in the context of connections with people doing quantum gravity, I want to be extremely careful. I want to urge carefulness with the use of the word causal. People mean very different things by the word causal. In particular, let me make a few comments to make it more precise what I mean by causal structure here. One of the most important comments is that this is time symmetric. This is not one of these notions of causation rather than causal structure that you usually have where A causes B, but B cannot cause A. Here, if you look at things in reverse, this is time symmetric. You would see that A not influencing D in U is the same thing as D not influencing A in U dagger. So that should make Keller-Ravelli happy. Second thing is that this should not be confused with a relativistic causal structure. Here, there is no background spacetime. We are only talking about an informational notion about influences between qubits, for instance, or more generally quantum systems. It's the interplay between this and relativistic causal structure is something precisely that that's the work I'm going to present talks about. Finally, this is model independent, by which I mean that this is not written in a particular theory of physics. This is not written in like a particular QFT or a particular kind of scalar field theory or whatever. These are just general unitary channels that could be anything. They are not obtained from a preferred Lagrangian or preferred Hamiltonian or anything. This is much more general than this. Okay, so that was just to give a general background about this idea of taking causal structure seriously in quantum theory. Now, let me explain why causal decompositions in that context are a particularly important question. So let me start with a simple example. With this example that I presented as an example of causal structure, where you have a unitary channel with a certain input not affecting a certain output, and that being the causal structure of U. This causal structure you can understand as an operational or phenomenological way of pinning it down, because A here, saying that A doesn't influence D can be really translated into operations you could do in the lab, where you tweak in some way the state A before you plug it into a component that applies U, and then you do measurements on D, and you will never find any dependence on your measurement outcomes in D on whatever you did in A. So this notion of causal structure is directly related to the operational data you can obtain. Let me now present another notion, which I will call compositional structure. Compositional structure is the statement that U can be rewritten as on the right-hand side, as the composition along a certain graph of two unitary operations U1 and U2. Here, what should be obvious is that the right-hand side implies the left-hand side. If U has a decomposition as in the right-hand side, you see that there is no way A can affect D there because there is no path from A to D. What is really interesting is that the left-hand side also implies the right-hand side. This has been proven a while ago. And so, in fact, these are equivalent statements to be made about U. But the right-hand statement is very different. It's about compositional structure, which is just a mathematical structural statement you can make about U. It's not directly related in particular to operations you can do in the lab. Okay, let me give another example, which has been recently proven, which shows that there is a hope to extend this to more general cases. If you take a unitary with 3 inputs and 3 outputs, and you can consider a causal structure where the left-hand one doesn't affect the right-hand one, and the right-hand one doesn't affect the left-hand one. This causal structure is equivalent with the existence of a certain decomposition of your unitary as in the right-hand side, where you now indeed see in the compositional structure that the left-hand input has no way of affecting the right-hand input, and symmetrically. An important thing to mention is that, in fact, this compositional structure in that case cannot be expressed in terms of unitary circuits. It has to be expressed in terms of fruited circuits, which is shown by which you can for which a typical property will be the appearance of these superscripts k that are being repeated. So I'm not going to go into the details of what that means. Let me say in a nutshell that this corresponds to the appearance of Hilbert spaces whose parallel composition does not correspond to a tensor product, but to a weird mix of direct sums and tensor products. But I'm going to explain more the structural reason for the appearance of this extended notion of circuits in that case. But if you allow yourself to go to the theory of fruited unitary circuits, then you still find this equivalence between the causal structure of a unitary channel and its compositional structure. So the general conjecture, therefore, of causal decompositions is that in general, you always have an equivalence between these two structures of quantum theory. And of course, that the right hand implies the left-hand side is just a statement about your compositional structure being worthy of that name. What is really important is to prove that a causal structure, at least in a good circuit theory, implies a certain compositional structure. So why is that interesting? Well, I already alluded to this. This is because these are seemingly very different structures of quantum theory. One is about lab operations. This is about what I can probe at the phenomenological level. The other one, it's really about the fine-grained dynamics that could be going on deep down in the universe. To further the point, one causal structure, it is extremely direct in the sense that it directly relates to your lab operations, but it's very fuzzy. It's not something you can easily handle mathematically speaking. There is no, if I tell you in U, A cannot affect D, there is no clear view you have of what kind of structure you could have. On the other hand, compositional structure is something very sharp. It's very easy to manipulate and it's constructive. It tells you, well, you can build out of these smaller operations, but it is not operational. And to drive the point further, I think there is a good argument to be made that, at least at a certain level, causal structure is about quantum information, and compositional structure is about some form of relativity in an extremely discretized and simplified way. It is about an underlying graph that could be going on beneath your unitary. And in that sense, I find the conjecture of causal decomposition as a very important way to explore the relationship between quantum information and the structure of spacetime. Hence why I am happy to be presenting it at this seminar. Okay, so now the thing is, causal decompositions have only been proven in a handful of cases for now. And in general, they remain a conjecture. So I'm now going to explain why system algebraic methods are important to investigate this conjecture. Okay, so I will make a detour through the theory of system algebras, but I have to start with a warning, a disclaimer for the KISS audience, which I know can be a lot from algebraic QFT or quantum gravity or general relativity. which is not my field. I am from quantum information, and therefore I want to say as a disclaimer, I'm going to present some stuff about sister algebras, saying it's great and so on, and this might sound trivial to you. And I am aware of this. It's just that coming from a different community, it's important to explain these notions to these people. All right, so let me start with a bit of basic mereology. Mereology is a very snobbish word that philosophers use to describe the relationships between the whole and the part. And there are two ways you could do mereology in physics. You can essentially do it bottom up. That is, you do it compositionally. That is, you say, in my theory, my parts are kind of prior, and then I have a way of composing them together. For instance, I have two particles, I use the tensor product, I get the system of the two particles together. There is another way of doing mereology, which is top-down. That is, you say, I start with the whole universe, and then I start arguing that for some reason or another, I can identify subsystems within my universe. For instance, bottom-up is typically what people do in quantum information. From my limited understanding, I think it is way more common in fields like QFT or quantum gravity to work top-down, to start with the block universe, the whole state of the universe, and then to start carving out stuff out of this. But in quantum information, bottom-up is way more common, and that's why here my point is to stress that it is important to also be able to do top-down. And let us see how this works in the quantum theory. So in quantum theory, usually, at least when you're restricting to finite dimensional systems, which, by the way, I am doing through this whole talk, you work with Hilbert spaces. And in Hilbert spaces, you can do bottom-up, of course, very easily because you use the tensor product. If I have the system A and the system B, I just have to get the tensor product of their two Hilbert spaces to get the space of their composition. Working top-down is way more awkward in quantum theory if you use Hilbert spaces. There is no nice structural way to pin down A as living within omega in the Hilbert space picture. On the other hand, there is something you can do that makes it way less awkward, and that is using sister algebras. If I use sister algebras, I can certainly say nicely what I mean by taking subsystems. So what is a sister algebra? A sister algebra is just an algebra of operators. And in infinite dimension, you can have sister algebras, one-domain algebras, but to me that's the same thing because this is finite dimensional. Infinite dimension, this is just a complex algebra with a dagger. There is a norm, but in finite dimension it doesn't really matter. And the way you should think about it is as the algebra of operators onto your Hilbert space. That's what connects the two pictures. So rather than caring about the state so much, you care about the operations that people could do. Okay, and in sister algebras, you can still work bottom up. You still have a tensor product. Everything works nicely. The great thing is that you can work top down. If I have the sister algebra omega of operations on the whole universe, if you want, I can identify the sister algebra corresponding to a subsystem by just looking at the operations that act on this subsystem and leave the other subsystem be invariant. And the way it works is that I just take a subsister algebra. I take A as any subsister algebra of omega, and B, the complement of A, I take as A prime, which is the commutant of A. That is the set of operations that commute with all the operations in A. That gives me a very neat, very natural mathematical way of pinning down how to carve subsystems out of the universe in quantum theory using sister algebras. Let me show why this connects nicely to quantum causal structure, which is what we were interested in. In finite dimension, at least, if I look at a unitary channel from two inputs to two outputs, I can look at it in the top-down perspective as just relating two sister algebras, but then saying that in my input sister algebra, I have a certain bipartition. I have a certain pair of these commutants of algebras that I just identified, which are A and B. And in the output, I have another pair of commutants of algebras. And U is just an algebra isomorphism. I see it rather as, the action of U by conjugation on this sister algebra, and it just preserves the whole sister algebraic structure. Okay. That leads me to something I will call the passive picture of quantum causal structure. I will not see U as something active that maps you from one state to the other. I will rather see it as specifying the relationship between two pairs of subalgebras of the same global algebra. So what I'm saying here is that rather than looking at Q, I'm going to say I have a whole algebra omega, and I have two ways to split it into. I have one way in which I split it into A on the one hand and B on the other hand, and one way in which I split it into C on the one hand and D on the other hand. And then I can express causal structure very nicely in that picture. Because for instance, if I want to say that A doesn't influence D through U, this becomes the statement that the algebra A and the algebra D always commute. And that is the same thing as saying that A is included in the algebra C and that D is included in the algebra B, because these are precisely the commutants. So causal structure finds a very natural expression once you start using system algebras. And precisely then that helps you prove causal decomposition. So let me take this simplest example and show that in this example, causal decomposition becomes almost tautological once you see it from the system algebraic perspective. So let me show how saying that A doesn't affect D in this unitary translates in the passive picture. I have a whole algebra of omega, and then I say, okay, I have one way of partitioning it into A and B, and I have another way of partitioning it into C and D. And the point is that A is included in C and D is included in B. Once you have this, it takes two lines of algebra to say that you can identify a third algebra, kind of in the middle, which is the intersection of B and C. And as an intersection of system algebras, it is necessarily an algebra. Therefore, you get a tripartition into A, B intersected with C, and D. And this tripartition is nothing but what you see on the left. In particular, B intersected with C is nothing but this kind of wire, this algebra that you see in the middle of that decomposition. And more generally, in the middle of that graph, you see three wires, A on the left, D on the right, and in the middle, this is B intersected with C. So my point is, in the passive picture, this just becomes a problem of free partitioning, finding this tripartition that stands in the middle. And once you have this, you are done. The rest is just bookkeeping. That leads me to this idea that causal decompositions, once seen from the mathematical perspective, are just a problem of fine-grained partitions. You have different partitions of the same space, and you start saying, okay, they relate in that specific way. And from that, I will infer that I have a common partition that kind of contains them both. Okay, and then you can reason with system algebras, which feels amazing. It is extremely abstract, it is extremely nice. Okay, there is a stumbling block though, which is the existence of non-factor system algebras. So let me just go back to the basics of system algebras in finite dimension. In finite dimension, a system algebra can be a factor, and a factor is a space of matrices. That is, this is just isomorphic to the space of linear operators of a certain Hilbert space. The general case, though, in finite dimension is a bit more involved than this. It's given by the Wedderburn-Artin theorem, which tells you that omega could also be a direct sum of factors, a direct sum of operators over Hilbert spaces. And this corresponds to system algebras of block diagonal matrices. If I look at the system algebra that you can see on the right, it is also a system algebra. You can check that it is closed under addition and composition and the dagger. Yet it is not an algebra of matrices. It is a direct sum of the algebra of the matrices on the upper left corner and the algebra of matrices on the bottom right corner. And if you remember that I was showing you this causal decomposition with these weird K superscripts appearing, these K superscripts precisely come from the appearance of non-factor system algebras once you start studying complicated enough causal decompositions. Because it's essentially a game of intersecting algebras, and eventually there is no reason you shouldn't end up getting a non-factor one. And that leads to complications because the case of non-factor system algebras, in fact, makes many things subtle to define. And in particular, this leads to the question of what even is a partition in this case. And that leads me to a whole detour through a general theory of what it means to take partitions of systems. In particular, when you have non-factor system algebras at play. So just as a reminder, the basic idea is that a good physical subsystem corresponds to a subsystem algebra. This is and I want to stress this is by no mean a new idea. This is something that is the bread and butter of algebraic QFT, but in a very different context, in infinite dimension, with kind of a preferred model, a preferred QFT. This is also something that has been advocated in quantum error corrections, in particular in the early papers. And there are also nice operational approaches that advocate this way of thinking. For instance, there's a very nice paper by Giulio Curibella to that effect. Okay, let us take a closer look in particular at the case of non-factor system algebras. Non-factor system algebras are characterized mathematically by the existence of a non-trivial center. The center of an algebra is a set of elements that commute with all of it. So the identity of the algebra is always in there. And in a factor algebra, in fact, this is the only element in it. The case of block diagonal matrices of non-factor system algebras is slightly more involved, because if I look at the projector onto the top left corner, for instance, you can check that it in fact commutes with everything in the system algebra. So the center is not trivial, and in fact, the center is precisely spanned by the projectors of the sort of the one I just referred to. So the center precisely tells you what are the blocks, because it is precisely the span of these projectors onto each of the blocks. That's how we should think of it. Okay. Now, as I said, there is a mathematical argument to be said that there is no reason to bar non-factor system algebras from corresponding to physical systems. But of course, we should try to link it to actual physical subsystems that we could find. Now, I like to make the argument that these physical subsystems are easier to find than one might think. Let me take a typical example, which is the superposition of trajectories. It's a very simple case, which is the following scenario. You can see at the bottom, I have two subsystems, M and C. I have a message system and a control system. And the control system is a qubit that will determine where the message system goes. Does it go through a left-hand channel in the possession of Alice, or through a right-hand channel in the possession of Bob? Now, if you try to model this scenario and model it in a unitary way, because you don't want to take in arbitrary other external systems, you want to stay within this universe of M tensor C, then you make the following discovery, that the channel of Alice, V1, you cannot model as just a channel on the possible states of the message, because Alice might get a vacuum state in case the qubit sends the message through Bob. And therefore, Alice's Hilbert space, for instance, you have to describe as the direct sum of a one-dimensional vacuum sector, HA0, and a d-dimensional message sector, which corresponds to the possible states of the message. But this way you can model that Alice possibly gets the vacuum. Possibly she gets nothing, but this nothingness is important in a sense. And for the whole scenario to make sense, you want to say that there is only one message in total. And therefore you want to put the condition that V1 cannot create or destroy a message. Therefore, V1 has to map the vacuum to the vacuum and the possible message states to message states. Therefore, V1 has to be block diagonal. And there are other subtleties to that argument, but then you see why it makes sense to say that to the extent that we believe that Alice and Bob have access to subsystems of the whole system, which makes sense. I mean, they are looking at it, they are doing operations on it that commute with each other. There is a good argument to be made that they have access to these subsystems, and these subsystems correspond to non-factor C-star subalgebras of the whole system. This is something, of course, that might remind some of you of superselection rules, the Aharonov-Bohm effect. It's definitely related, but I don't want to make too strong claims about this because there are subtleties, and this is not the point of my work for now. Let me just show you one disturbing feature you get by working with non-factor C-star subalgebras. It's called, we decided to call it failure of local tomography, or fault for short, which is a very apt name in my opinion. So if I take once again this example of the superposition of trajectories, you can in fact find this feature at two levels, at the mathematical level, at the operational level, and these are really two faces of the same coin. At the mathematical level, what you find is that if you take the algebras A and B and you take the algebraic span, you do not recover the whole algebra. And the reason is both are block diagonal, and even if you take them together, they can never beat the block diagonalness. And that means essentially they can never recover operations that would change where the particle is. And at the operational level, this corresponds to the fact that if Alice and Bob, who have access respectively to V1 and V2, start collecting data, they start doing tomography. So they start using V1 and V2 to do measurements and find and even look at the correlations between the measurements, collect data, find the exact statistics. They will never be able to find out the relative phase between their paths, because that would essentially correspond to these operations that are not in the span of A and B. So this relative phase makes no sense from the joint perspectives of A and B, even though it is accessible to global agents. If you act on MC, you can do anything you want, and in particular, you can measure that phase, which is the phase between the two states of the qubit. So that's failure of local tomography. And if you want to work with non-factor system subalgebras, this is a bullet you have to bite, really. Either you don't like it, and then you just essentially ask for your algebras to all be factors. But this is saying that fault appears is almost the same as saying that non-factor system algebras appear. Okay, and then that led us into a whole rabbit hole of wondering, in fact, how can you do a theory of partitions with non-factor system subalgebras? And as I showed, this actually leads to many complications. So in particular, the goal was to do it for more than 3 parts. Here I showed examples of bipartitions, which are kind of manageable. Once you go into more than 3 parts, what we found was that it's actually very subtle because of non-factorness and because of fault. So I'm not going to go into this. I present this in the other paper and in the other talks that you can access. But the idea is that eventually we managed to overcome this and to provide a well-defined and a consistent theory of partitions for into any number of subsystems. And one thing that we are excited about is that its non-trivialness also corresponds to the existence of very interesting mathematical structure. And this mathematical structure, we think, could also correspond to nice physical structure and to applications in many other domains. And we have a few in mind already. But this was a whole detour, and we need to go back to our question, which was that of the existence of causal decompositions. Okay, so, and I'm going to explain how in the upcoming paper, we prove that this yields causal decompositions for 1D quantum cellular automata. So what is a 1D quantum cellular automata? The idea is just that it is a unitary operation onto a certain number of sites. So each site is a Hilbert space, and in particular, in 1D, you say that the sites are disposed along a line. The line becomes important because you say that this unitary has a certain causality radius. This causality radius tells you that through the unitary, a certain site only affects its neighboring sites. For instance, here, this is causality radius 1. So an action on these inputs would only affect the outcome on these 3 outputs, but not further away. And you can take any causality radius. A few technical things to mention is that usually people take 1D QCAs to be translation invariant, and to us this is unnecessary. We can even work with non-translation invariant ones. There is a question of topology of your 1D line, so it can also be looped around in a circle. And for us, the result I'm going to present also works if you loop it around in a circle. One limitation we have, though, is that we wanted to keep to the finite dimensional realm, and therefore we restrict it to a finite number of sites. If you have an infinite number of sites, of course, your linear dimension of your Hilbert space becomes infinite. And that leads to mathematical complications, and we didn't want to get into that for now, even though this is definitely a direction for the future. And why do people care about 1D QCAs? It is because they are models of spacetime. It's essentially, if you discretize your spacetime, you can say that, for instance, a 1 plus 1D Minkowski spacetime is nothing but a 1D QCA. This is, you're looking at the dynamics inside your 1 plus 1D spacetime, and you're saying that it has to satisfy the Minkowski, the lightcone, the Minkowski structure. And so precisely a certain actions at a certain location in spacetime cannot affect locations of spacetime too far away from it. So if you discretize your spacetime, the dynamics in it is described by 1D QCAs. And for that reason, also people took it to be a very fundamental model of quantum computation. Okay, in particular, people have found an interesting result for 1D QCAs of radius 1/2. So you can take the case of radius 1/2 by slightly shifting your output yielded sites with respect to your input sites. And in that case, you can prove, this has been stated in a different way, but this is essentially the statement, that these 1D QCAs are only the unitaries that can be built in the form that you can see at the bottom. And yeah, people state this in a different way, but this is nothing but a causal decomposition, right? The existence of the causal structure, as in the above, is equivalent to the existence of the compositional structure, as in what you can see below. And this is very interesting also for another reason, which is that it is a constructive form for 1D QCA. If I tell you, give me a 1D quantum cellular automaton, you can take your favorite unitary channel and then painfully maybe check that it features the no influence, it satisfies the no influence condition given by the causality radius. But a constructive form is much more informative. If I tell you, give me a 1D QCA with radius 1/2, you now know you only need to pick your favorite operations and compose them along this graph. And this will span the exact, all the possible cases, the exact span of possible cases for 1D QCAs, because this is the same thing. That's the theorem. Okay. And this is also related to index theory and things people care about in the field of QCAs. Okay, that still leaves open the question of higher radii. And just to make a comment about what people say in the community, there's a certain statement that in 1D QCAs, this is okay because you just need to regroup sites, and that maps you back to QCA of radius 1/2. However, to the extent that you are interested in constructive forms, this doesn't work, because if I apply then the theorem to the QCA of radius 1/2 that I obtained, I get this. And this has apparent radius 3/2. In other words, the result for the radius 1/2 does not exhaust the possibilities. In particular here, it does not give you all and only the QCAs of radius 1. You just get QCAs of radius 3/2, really. So the question was still open for higher radii. But we closed it because this is finally our result. So after this whole trip, I can tell you that using C-star algebras, you can unlock, and it is quite structurally interesting. I mean, it is not direct, but it involves a very nice mathematical result. You can unlock this proof that 1D QCAs are causally decomposable at any causality radius. So for instance, for a 1D QCA of radius 1, saying that U is a 1D QCA of radius 1 is exactly the same thing as saying that A can be decomposed in that way. Here you again see these K superscripts that correspond to the fact that it has to be written in rooted unitary circuit due to the appearance of non-factor subalgebra. And this works at any radius. If I take radius 3/2, then saying that U has radius 3/2 is the same thing as saying that it can be decomposed in that way. And this extends unless the only caveat is that if you're working on a loop, the size of your loop has to be more than 4 times the causality radius, because at some point your topology goes back to you know, the lichens start intersecting on either end of your universe. Okay, so that's the result. And what are the implications? The implications, I think, are and that's also where I want to make the connection between quantum information and the structure of spacetime. This is really a theorem about what are the causal dynamics in 1 plus 1D spacetime. In a discretized case, there, but that's already something. And there are 2 ways you could say your dynamics are causal in your 1 plus 1D spacetime. There's a way in which you could say just operationally, you don't have influences outside of the light cone on the one hand. On the other hand, you could say they are built out of nearest neighbor interactions. They are local in an undefined grain level. And these two ways I described are just causal structure on the one hand and compositional structure on the other hand. And this result shows that at least in one spatial dimension, this is the same thing. These structures that look very different are two faces of the same coin. So I think this is a very important structural result for the structure of spacetime. In particular, it points to a very important research program to investigate whether and how this extends to higher dimension. More down to the ground, you have this also can be seen as a result of providing a constructive form for 1D QCA. So rather than having these operational properties that you have to check on these QCAs, suddenly you know exactly their inner structure. That gives you a very nice handle on them to investigate their property. Okay, so time to wrap up. Let me mention some lessons from that talk. First lesson, I hope that you are all convinced now, is that causal decompositions are cool. A second lesson is that they are mathematically nothing but a problem of fine-graining partitions. That's how you should investigate them mathematically, using the top-down perspective on subsystems. The third lesson is that we would be wise to pay more attention to non-factor sister algebras, at least the quantum information people among us, because probably some of the QFT or quantum gravity people were aware of that already. And finally, the technical result here is that, to put it in extremely high-level terms, you have two formulations of relativistic causality in spacetime. You have a phenomenological one saying, I just cannot find influences outside of the light cone in my spacetime. And the other one is that it's more ontological in the sense that my spacetime is just built out of nearest neighbor interactions. So really, I can see the information never leaving the light cone, even at the fine-grained level in my spacetime. At least in one spatial dimension, these are equivalent. These are the same thing in the discretized case. But that points to possible extensions to higher dimensions and the continuous case. Okay, and that also leads to many prospects, as I said, precisely investigating the spatial temporal relevance, linking it with the properties of 1 plus 1D spacetimes, using these algebraic methods for other uses. I have in mind the classification of other nice types of unitaries, dual unitaries, perfect tensors, using this theory of partitions for other aims, in particular superselection rules, the Aharonov-Bohm effect, and we are currently also investigating nice application to the theory of quantum reference frames. And finally, of course, pushing causal decompositions further because they still haven't been proven in general case. Now, something I was a bit sneaky about is that we actually found a counterexample to causal decomposition. But this counterexample is about causal decompositions in the theory of fruited unitary circuits. And potentially, there is an even wider theory of circuits that would still be able to carry on the idea of causal decomposition, and that would also tell us way more about the inner structure of quantum theory. So the hope is not dead. And even if this counterexample still holds, it is a very important one to study, of course. That ends the talk. I want to thank my coworkers Pablo and Octave again, and thank you all for staying with me.
Okay, fantastic. If we can all thank Augustin for what was a really nice talk. And if anyone has any questions, please just raise your hands and I'll come to you. And if you're not able to ask questions for audio reasons or anything, then feel free just to type them in the chat. So we'll begin. I see Hannah Seabrook.
No, sorry, I was just uploading.
Oh, okay, yes.
Thanks for the nice talk.
Thank you.
Yes, I'm sorry if I mispronounced the name.
Radhakrishnan. Yeah,
Radhakrishnan. Great,
okay.
Thank you.
All right. So you are dealing with the finite dimensional systems, right?
Mm-hmm.
So everything you can do with the C-star algebra can be done with tensoring of Hilbert spaces, except the non-factor C-star algebra. So
Precisely.
that's what I'm trying to understand. So the non-factor algebra. So the okay. So the center of that algebra is non-trivial.
Yeah.
Okay. So operationally, how do you achieve it? Because you are entangling the subsystems, or how does the non-factor comes into play?
Well, I mean, maybe I can come back to my physical example precisely. You get it operationally, it's a kind of entanglement if you want, but you also get it from assumptions about what kind of system you want to consider in the first place. So if I take this superposition of trajectories, what I'm saying is that what I want to consider is the system corresponding of the message and the qubit. And in particular, this system, after the message has gone into a superposition, corresponds to the message being in the possession of Alice and the vacuum in the possession of Bob, or the other way around, the message for Bob and the vacuum for Alice. And if you go down that path, it is natural to say that Alice and Bob have access to non-factor subalgebras of this whole system.
Yeah, okay, I see it. Yeah, even superposition is good enough to get the non-factors. Okay, yeah, thank you.
You're welcome.
Okay, so I don't see any more questions yet, so I'll ask. No, I do. Okay, Ding.
Hello, thank you for the nice talk. You compared decompositional perspective and causal structure perspective, and you contrast this with the operational approach, quantum information on the causal structure side and fundamental physics on the decompositional side. I'm curious about the relevance of the rooted structure, the non-factorization, to the fundamental physics side. For example, for this circuit you show on the slide, you some operational procedure to realize this in the lab. But then again, at the fundamental physics side, I'm not sure how I should describe it, for example, at the level of relativistic quantum theory. Is it possible to have a factorized description of the same physical situation? For example, if I want to have a QFT description with the same phenomenology, I'm not sure if it is possible to get rid of the rooted structure. I'm just curious what your thought on this.
Yeah, thanks for the question, and good to see you, by the way. It's a very good question, and indeed, that's a true argument, at least for these finite dimensional kind of vanilla examples I took. You can always get rid of this direct sum structure and embed yourself inside a larger space in which you will only be using the tensor product structure. Here, and you can see it in this example. You can just embed yourself inside a larger universe of just Alice having the vacuum or the message, and Bob having a vacuum or a message, and you just take the tensor product. Therefore, it's Alice and Bob, and they can have one message or no message or two messages. And the only problem is that if you do that, you're suddenly not considering subsystems of the same system. Suddenly you're embedding yourself inside a larger system. And in particular, for the problem of causal decompositions, you see that once you start doing this, you're not unitary and you lose track of your whole structure, and technically you will not go through. Now, your question, of course, was about the application to fundamental physics. I think your counter-argument is, of course, extremely correct, and we have to keep it in mind. I still think there is an avenue to explore to forbid yourself from doing that and see where that leads. For me, for causal decompositions, it really helped. And I think there are interesting things to find down that road. But of course, yeah, you have to keep in mind that as far as applications to fundamental physics are concerned, we need to take into account this ability to always embed yourself inside your tensor product.
Yeah, thank you. Can I ask another question?
Go for it.
Yeah. This question is about cellular automata for your result in the main theorem you showed
Mhm.
the cellular automata, the quantum cellular automata, you can always do decomposition into rooted circuit. I'm just wondering if there are any already existing applications of this type of rooted cellular automata, because in my limited knowledge of the subject, the cellular automata I see are always, just tile up a bunch of unitaries without the subspace structure, just tensor product structure. And do you know any existing examples using the routing structure?
No, also for the reason that we are kind of expressing them for the first time, at least in that language, in that paper, to just express the decompositions. I wouldn't be surprised though if typically fermionic QCAs, I haven't looked into the subject that much. I'm actually not that literate about QCAs, so I don't want to say anything stupid, but maybe for instance the fermionic ones or quantum walks as well, which are a specific type of QCA, they could be seen as being rooted circuits in disguise, because you do in a quantum work, you only have one particle in total, and that will be similar to this superposition of trajectories thing. In fermionic QCAs, you will have super selection rules all over the place, and I think it will relate to kind of the structure that we found there. So maybe some examples are there in disguise, but I wouldn't be sure.
Thank you.
Thank you. These are great questions.
Okay, I have a question. Okay, so you use you kind of argue that okay, you don't have a causal decomposition in terms of tensor product factorizations everywhere. You do in terms of kind of C-star algebra subsystems. And you point out that these C-star algebra subsystems seem very physically reasonable and naturable, have a nice interpretation. So kind of taking the opposite road to ding, like what if I just naively say, okay, I agree with you, like subsystems are C-star algebras. What happens if I'm trying to take those as the inputs and outputs to my global unitary? So I have some global unitary and I want to study its causality constraints and what I think are the most general kind of subsystem, which are not, because the inputs and outputs to this thing are still tensor factorizations, right? So is there a reason to not take that question so seriously? Or if you think you should take that question as seriously, then do you have any thoughts about what will happen?
I think you should, and I think you might find surprising effects. And in particular, I would like at some point to extend these results to fermionic quantum cellular automata. And as I was saying to Ding as well, I think this is precisely you will precisely find non-factor subalgebras because you have super selection rule. And then I think I've vaguely heard of people actually already having found weird fermionic QCAs, and I suspect that weirdness can be related to maybe the non-existence or the non-existence of causal decompositions, or maybe causal decompositions not being expressible at the Hilbert space level, which might be also an issue, but I won't get into that. So yeah, I think this is a great avenue to explore, and I'd love to do that later.
Okay. And okay, if in higher dimension, you can find some global unitary that doesn't have some nice decomposition into any notion that anyone can imagine of local gates. And the kind of claim is that the only thing you can probe is the causal structure, and that the compositional structure is a mathematical thing. Like, what do you make of those global unitaries? Do you find this as a reason to think that like they might not exist?
Sorry, what do you mean by the global unitary?
Okay, so you have some global unitary with signaling causality constraints, and let's say we're in higher spatial dimension, and let's say you find one that just has no notion of decomposition into local gates of any kind. Like, if the claim really is that the only thing you can access is the is the causal structure? Like, does this change your opinion on the implementability of that unitary, for instance?
That's a great question. I think this really opens now a rift between these two notions of relativistic causality, and it is not clear, at least in my opinion, which one you should pick, and then it becomes really interesting. To me, it's a win-win game. You know, if you prove causal decompositions, it's cool. If you prove they're non-existent, it's cool as well, because suddenly you have these weird ambiguities in how you should phrase things. Should you use one way or the other to say what could be going on? What is an acceptable unitary in that causal structure in that space-time? So I don't know, and I think this is a very important question.
Okay. Okay, cool. Are there any other questions in the chat? Let's just see. We'll just give people a second to ask any more questions.
So can I ask a second question?
Yeah, please.
Okay, so if you have factors, you can build all the towers, like, you know, the sub-factors, the theory. So you can build an infinite towers that leads to all these projections. They have this braiding relationship. But with the non-factors, that may not be an option. So do you have any thoughts on that?
I'm not sure. You might be mentioning a concept that is important for infinite dimension, right?
Yes, of course, yes.
Yeah. And I am shamefully illiterate about infinite dimension. I've taken it as a methodological principle to stick to finite dimension, because this is already quite involved to prove infinite dimension, and to at some point I will learn about infinite dimension, see what goes on there.
Yeah. So
I mean,
what your framework will work for infinite dimension so long as it's a countable and infinite. Yeah. So
that's my hope. But there will be, of course, subtleties probably improving it. But I think there's no reason it shouldn't work.
Something to think about. Okay, thank you.
Thank you.
Why would it be so would it be especially bad if it was an accountable infinity then?
For countable infinity, it should generalize in a straightforward manner, right? So from finite dimension to countable infinite dimension, you can push all the proofs. I don't see a problem. But other cases would be a problem. Yep. So I mean, taking the tensor, continuous tensor itself will create other problems. So if you have uncountable infinity, so if you have an uncountable infinite Hilbert spaces, right? Tensoring them will create more technical issues. And then defining the algebras, subalgebras that are not factors, that is tough. So in one-dimensional algebras, any one-dimensional algebra can be decomposed into disjoint union of factors. But here, when you have non-factors, I haven't thought about how it will decompose.
Okay. So I'm just taking a look to see if there are any more questions. Feel free just to speak up, because we have no hands up.
This talk would be available on YouTube or something? This presentation?
Yes.
Okay.
Yes. So it's been recorded and it's also been live streamed. So as soon as it's over, you should be able to find it. Yeah.
And it will take a few days before it will be available?
It should be there right now.
Oh, okay. Thank you.
I think we are on YouTube right now.
Yes, we are on YouTube. Yes, exactly. Yes. Good. Okay. So, I don't think I see any more questions. So I think this is a good point to say, yeah, thank you very much, Augustin, for a really lovely talk. Yeah, if everyone wants to unmute and clap or thank Augustin, however you feel. And yeah, thank you. And we'll see you all at the next session.
Thank you.
Thank you, Augustin. I appreciate it.